Hi guys, welcome to this recording concerning one of the problems in our discussion that we did 2 days ago on Wednesday concerning one of the problems. Apparently there was another part to it that we didn't complete, so the purpose of this recording is to just complete that part. Because it was on the second page and I thought that we were done with that problem, so we're not. Anyway, the first part was to check to see if this wave function, namely for the 1s state for the hydrogen atom given by that expression. I'm going to, for the moment, ignore this. We can keep it. Okay, it's the scaling factor minus r over a naught. So this is the wave function in the 1s state for the hydrogen atom. We checked from the previous problem to see that indeed it was a solution to Schrödinger's equation where the energy was correspondent to the ground state energy of the hydrogen atom, and also the fact that it's the radius in this case turned out to be equal to a naught given by Bohr's expression. So we did that, and also we checked that again it's normalized, but there was another part to it that I didn't know. It was brought to my attention actually, to see what is the probability of finding the hydrogen atom or the electron between positions a naught over 2 and r2, which is equal to 3 a naught over 2. So basically half the Bohr's radius and about time and a half the Bohr's radius. So for that, since the wave function now is normalized, this probability is just given by the integral or between these two boundaries. So basically the probability of finding between R1 and R2 is simply going to be equal to the integral of the probability density, which is given by the square of this function now. And because it's all real, I mean, there is a complex part, but that complex part, and that is coming from the time part. So we're just focused on the spatial behavior of this wave function. The integral is between R1 and R2, and in this case, the element of volume, it's a sphere. So 4 pi, I'm sorry, times R squared dr. So again, that's the element of volume. It's very important to make sure that you're working in the proper units, since we're in polar coordinates. That's what we need. Anyway, so the only thing that is different than the normalization integral is that that integral was from 0 to infinity. This integral is from R1 to R2. So everything carries the same. So that change of variable that we did last time still holds true, namely the fact that this probability, so I'm going to drop the index in here, but I'm going to assume that just we're calling from position 1 and 2. So that probability is, again, the boundaries of integration is from R1 to R2, and 1 over, in this case, pi a naught cubed. Okay, I'm looking at the book, by the way. This is the book that we're using. We're on page 1140, so that you have to follow with me. So it's exponential again of negative twice, because we're squaring now this wave function over a naught times 4 pi r squared dr. Of course, the pi cancels the pi, and we're going to do that same change of variable that we did in class, namely y is equal to 2r over a naught, which means that dr in this case is equal to dy times a naught divided by 2. Okay, so the exponential now will have y in it, negative y that is, and then here you have 4r squared over a naught squared, that is actually y squared, but we have that dr that's going to bring this a naught, which cancels the other a naught from the a naught cubed, so we'll be left with 1/2 of everything in here, the same as we did the normalization. So basically what we're left with in this case is this probability is going to be equal to the integral. Now the boundaries of integration change because the value of R1 is equal to a naught over 2. That means that you have an a naught over 2, the 2 cancels the 2 in the a. So y is going to integrate from 1, because this becomes 1, and 3 over 2, so it's going to be y equals to 3. So the boundaries of integration as far as y is going to be just from 1 to 3. Okay, so we're going to end up with a number at the end of the day because the boundaries of integration become just definite numbers, and the whole thing does not depend on A naught. And that's good because we want probability, we want it to a specific number. So again, we're going to have 1/2 coming from the dr time y squared exponential of negative y dy. Everything is the same. Now we're going to do this integration again by parts twice, and each time we're going to, but you have to be careful in here. Unlike before, where the integral by parts, the first part, the complete part was 0, though it's not. So let's do that. So the first part in here is going to be 1/2 the function y squared and the antiderivative of negative exponential of negative y, which is this one. And the boundaries of integration is 1 infinity. Before it was 0 infinity and the value was 0 on both ends. Now it's not. Okay, minus minus, so it's going to be plus the integral from 1 to 3, I'm sorry, of the derivative of y squared is 2y, cancels the y, so exponential of negative y dy. I mean, cancels the 2, that is 2y squared over 2, so that's going to cancel the 2. Now, so this part that was 0 before, now it's not 0 anymore. Okay, so this part in here is 1/2 times 3 squared, that's 9, times negative, with a negative sign, exponential of negative 3, minus minus, so that's plus y squared, which is 1, exponential of negative 1. Okay, so this number is not 0. Okay, so this whole thing is not 0. It may be 0, but no, but it's not 0. So it's going to be a number. Okay, don't forget E is 2.71. Okay, the natural E. Okay, part of the natural log, I'm sorry. So this integral again is going to be done by parts. So it's going to be equal to y, negative exponential of negative y. And again, the boundaries of integration, not 0, I'm sorry. It's from 1 to 3. And now the last part in here, which is just minus minus, so it's going to be a positive. The integral from 1 to 3 still. Okay. Just the exponential now, like exponential negative y dy. Again, this is going to be just negative exponential of y from 1 to 3. So at the end of the day, this whole expression will be just a number. Okay, I'm going to leave it up to you guys to finish the numbers, because it's just basically the first part is 1/2 times, I'm going to put the positive number first, e to the negative 1 minus 9 e to the negative 3. Plus this part in here, I'm going to start with the lower end because that's a positive value, minus minus 1, minus minus 1 over e, that is. So it's going to be again e to the negative 1, that is, no 3 or anything like that. It's the second one that will have e to the negative 3. Okay, and finally, the last part in here is just with a 3 multiplying it. I'm sorry, because there is a y in front of it. So there is a y in here. Okay, good. Now the last part in here that I need to add, this is the last term in here, which is again, we're going to start for the lower end because it's the positive end. Exponential negative 1 minus exponential of minus 3. Anyway, so we're done. Okay, so you guys are going to, obviously this number is positive. Okay, because E1 over 2.7 minus 1 over 2.7 cubed. Okay, same thing, this number is going to be positive because E1 over 2.7, 1 over 3 minus 3 over 9, so it's going to be basically the same thing with this number. Actually, it's going to be, all of them are going to be positive, and they're all going to be between 0 and 1. So the probability is not going to be more than 100%, and it's not going to be a negative number. That makes sense. So I leave it up to you guys to finish this calculation. So that was what's missing in our discussion last time. Thank you.